All right. When we are dealing with basic organic nomenclature, there's a couple of items that we have to make sure that we make note of. First, we're going to deal with alkanes, alkenes, and alkynes. Alkanes is going to be saturated with single bonds, and this is the formula to determine your molecular structure. Then you have your alkenes, which is going to have one double bond, and the rest are going to be single bonds. And this is your equation for your molecular formula. Then you have your alkynes, which is going to have a triple bond, and the rest would be single bonds. And your formula for that, for your molecular structure, is this here. The next piece of information you need to make note of are going to be your prefixes. Your prefixes will let you know how many carbons you have per structure. So meth, of course, would be 1, F2, prop 3, but 4, pent 5, hex 6, hept 7, oct will be 8, non will be 9, and dec will be 10. So when we're doing these problems, the first thing we want to do is find out how many carbons and what type of bonds we're going to be doing. And we can do this quite simply by looking at the prefix and then our ending. So here we have prop, and if we go to our prefixes, we see that prop means there's going to be 3 carbons. And then we have ane. Ane, of course, is going to be saturated with single bonds. So in order for us to do the skeletal structure, we first draw all of our carbons. So we have 1, 2, 3. So that satisfies the prop. Now let's do the ane. That means we're going to fill in all of our bonds there. Now we are not completed because all of these carbons are going to be connected to hydrogens. And in this particular case, propanes or alkanes are saturated with single bonds. So each carbon is allowed 4 parking spaces. All right, so here we have 1. So let's go ahead and complete that, and that makes that 4. Then we go to our second carbon. There's already 2 bonds or 2 parking spaces taken. So we would fill that in with the other 2, meaning we have 1, 2, 3, and 4 around that carbon. And then our third carbon has just 1, so then we would fill that in with the other 3. And each of those, of course, would be attached to a hydrogen. And that there is our skeletal structure for propane. Now for our condensed formula, what we would do then is take a look at our first carbon and see that it is attached to 3 hydrogens. So that would be CH3, notating our single bond to our next carbon, which is attached to 2 hydrogens. So that in turn would be CH2. And then our third carbon is attached to 3 hydrogens. So once again, we have our single bond and our carbon with our 3 hydrogens. All right, and to satisfy our third portion of this problem, we have our molecular formula. And as you see here, we're going to use CnH2n plus 2. N is the number of carbons. So we want to make sure we keep that in mind when we're doing these problems. So now we're going to plug and chug our information. So we know N is going to be 3 because of the prop. So we have C3. Then we get to our hydrogens, which is 2 times N, and our number of carbons is 3, plus 2. We bring down our carbon, so C3 we have H. 2 times 3 is 6, plus 2 is 8. And we can check our work by going back to C. We have 3 carbons, 1, 2, 3, and 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. So we know our condensed and molecular structures match. And let's check our skeletal against this. 1, 2, 3 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that satisfies drawing skeletal, condensed, and molecular for alkanes. So let's take a look here at alkenes. We will do the same as we did before. But is going to be our prefix, so it lets us know we are now working with 4 carbons. And then our ending is "ene," and it lets us know we're dealing with 1 double bond, and the rest would be single bonds. So let's first draw out all of our carbons. 1, 2, 3, 4. And let's go ahead and satisfy that double bond. So we'll put that in the very beginning so we don't forget. With that being in place, go ahead and fill in your other single bonds. We are now going to add our bonds for our hydrogens. So looking at our first carbon, 2 parking spaces have already been used. 1, 2. Whether they're around the carbon, beside the carbon, you check how many have already been used. So we have 2 that have been used. So we're allowed to add 2 more. So there's 1, 2, 3, 4. Looking at our second carbon, you look to the left and the right just as if you're crossing the street. And there's 1, 2, 3. So we're allowed 1 more, making 4. Checking our third carbon, there's only 2. So we would fill in our other 2. And then we have our last carbon, which only has the 1. So we'll go ahead and fill in the 3. Go ahead and fill in our hydrogens. Okay. Moving down to our condensed formula, we take a look at the first carbon. We have 1 carbon and 2 hydrogens. And what the condensed formula does is gives us everything we see here just written on a linear line. So we would have our CH2. We need to use our double bond. Then we go to our next carbon, which only has 1 hydrogen attached. We have another bond. Our third carbon has 2 hydrogens. And then our bond, and then we have our last carbon, which has 3 hydrogens attached. We'll now move down to the third section of the problem, which is going to be your molecular. So you would use your formula of CN, H2N, and of course we know N is our number of carbons, so let's go ahead and fill in the information we have. We're dealing with 4, then we have H, 2 times N, or 2 times 4, which of course we bring down the C4, and then H, 2 times 4 is going to be 8. And we can go back and check this again. We have 4 carbons, 1, 2, 3, 4. And how many hydrogens? 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we know that our condensed and molecular match. And let's check our skeletal structure. We have 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we know that our skeletal, condensed, and molecular structures match. So let's take a look at our last and final organic structure, which is going to be an alkyne. All right, and our third And last organic structure is going to be our alkynes, which is going to have one triple bond, and the rest would end up being single bonds. So once again, we take a look. Our prefix is pent, meaning that we have 1, 2, 3, 4, 5 carbons. Then we have our ending in -ine, which lets us know we have a triple bond. And let's go ahead and draw this structure. Go ahead and fill in our carbons first. And now filling in our bond, starting with our 1 triple bond. And the rest are going to be saturated. So looking at our first carbon, of our 4 spaces that are allotted, we have 3 that are taken, so we're allowed 1 more. Let's take a look at our second carbon. There's 1, 2, 3, and 4. So there are no extra bonds allowed on that second carbon. It is completely full. Moving to our third carbon, there's 1, 2 bonds. We can have 2 more. Our fourth carbon, same thing, 1, 2, so we can have 2 more. And then our very last carbon only has 1, so we'll go ahead and fill in those 3. Go ahead, add your H's for your hydrogens. So there is the completion of your skeletal structure for pentine. Now let's do our condensed. Looking at our first carbon, we have only 1 hydrogen, so we would have CH. And remember, everything that is in the skeletal structure is needing to be notated in your condensed structure. So you would next fill in your triple bond, your second carbon, your single bond. Now you have your third carbon with 2 hydrogens. Your fourth carbon, once again, connected with a single bond that has 2 hydrogens. And now our fifth carbon has 3 hydrogens. All right, and that would be the condensed formula for our pentine. Now we're going to need to use our formula for the molecular section of the problem, which is going to be CnH2n minus 2. Because of your double and triple bonds, quite often you're not going to have as many hydrogens as you would on your alkanes, because those alkenes and alkynes are unsaturated, meaning that there are not as many hydrogens as absolutely possible. So once again, let's fill in our N, which is our number of carbons, which is 5. Then we have our hydrogen, which is 2 times N, or in this case 2 times 5, minus 2. Go ahead and bring down your carbons, which is C5. Then we have 2 times 5 is 10, minus 2 is going to be 8. So let's go ahead and check our work. Going up from molecular to condensed, it's stating I should have 5 carbons, 1, 2, 3, 4, 5, 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, and 8. And then we can check this all against our skeletal structure. 5 carbons, 1, 2, 3, 4, 5. And now your hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Now I will tell you, it is always in your best interest to go back and check your work as I did here, because there is quite often where you'll have too many carbons or too many hydrogens, and this is one set of problems that is very easy to check your work. I hope this helps.